Hey guys, this is Jason Matthew from Trinidad and Tobago, and welcome to the BiochemJM YouTube channel. So today we're going to be calculating the number of ATP generated from the oxidation of palmitate. So the exact question will come like this: calculate the net gain of ATP when palmitate is completely oxidized. Show all working and indicate any formulas, reactions, and metabolic processes you use to derive your answer. So at this stage, I will advise you to pause the video and go and try to work out the question on your own. And when you're finished, come back, look at the video and see my solution and see, if you got it or where you went wrong, and and make necessary adjustments. Alright, so you probably knew that palmitate is a fatty acid, but did you know that it is a 16 carbon saturated fatty acid? And that is important, knowing that it's an even carbon fatty acid, and also knowing that it's saturated as opposed to unsaturated. These factor in when you calculate the number of ATP. All right, and then the next thing you need to know, at least for animals, is that beta oxidation occurs in the mitochondrial matrix. So the first thing we need to do is to calculate the number of rounds of beta oxidation. And to do that, you use a general formula, n over 2 minus 1, where n is the number of carbons. So for palmitate, n will be 16, and 16 over 2 minus 1 will give you 7 rounds of beta oxidation. For each round of beta oxidation, you're going to get 1 NADH, 1 FADH2, and 1 acetyl-CoA, except for the last round, and that will make more sense in the slide to come. So based on this that we have here, we have 1 palmitate giving you 7 NADH, 7 FADH2, and 8 acetyl-CoA. So let's see, we have 7 rounds of beta oxidation, we have 7 NADH, 7 FADH2, and 8 acetyl-CoA. Wait a minute, 7, 7, 7, 8? Well, let's see. Let's look at an easier example. Let's look at a 6 carbon saturated fatty acid. So once again, we're going to be calculating number of rounds of oxidation. So for a 6 carbon saturated fatty acid, N will be 6. So 6 over 2 minus 1 will give you 2 rounds of beta oxidation. Now, those 2 rounds of beta oxidation will give us 2 NADH, 2 FADH2, and 3 acetyl-CoA. So remember that for each round of beta oxidation, you are removing 2 carbons from this fatty acid chain, and those 2 carbons are going to combine with CoA to form acetyl-CoA. So let's see what happens with these 2 rounds. So the first round, you break the bond, you get these 2 carbons, and that 2 carbons will form acetyl-CoA. Now when you do the second round, you're going to be breaking this bond. But you realize that when you break this bond, you get 2 carbons, but you also get another 2 carbons. And what will happen is that in that second round, you're actually going to get 2 acetyl-CoA molecules. So in total, you got 3 acetyl-CoA molecules. So one way to look at it is that, you always get 1 more acetyl-CoA than your number of NADH and FADH2. So like for instance, you had 7 NADH, 7 FADH2, and you got 8 acetyl-CoA. And down here, 2 NADH, 2 FADH2, 3 acetyl-CoA. So that's something to think about. So let's recap. Palmitate is giving us 7 NADH, 7 FADH2, and 8 acetyl-CoA from beta oxidation. Alright, so we need to understand what's going to happen to the acetyl-CoA. What's next? Well, each acetyl-CoA is going to enter the TCA cycle and go through a round of the TCA cycle. So for every 1 acetyl-CoA entering the TCA cycle, you're going to get 3 NADH, 1 FADH2, and 1 ATP. So if it's 8 acetyl-CoA molecules entering the TCA cycle, you're going to get 24 NADH, 8 FADH2, and 8 ATP. Now remember, you also have NADH and FADH2 from the actual beta oxidation. And so you're going to have to be summing up everything just now. So let's just do that. Let's see what we have. All right. So from the rungs of beta oxidation, you got 7 NADH, 7 FADH2. And from the TCA cycle, you got 24 NADH, 8 FADH2, and 8 ATP. So in total, so far, we have 31 NADH, 15 FADH2, and 8 ATP. All right, but our journey is not over. In fact, we have a lot of ATP still to account for. And that's where we go to oxidative phosphorylation, because NADH and FADH2 will go to the electron transport chain, and when it reaches the electron transport chain they're going to give up a pair of their electrons, and the electrons going to go through the electron transport chain. And for one NADH, you're going to get 3 ATP, and for one FADH2, you're going to get 2 ATP. So we had 31 NADH in total, so that's going to give us 93 ATP, and we had 15 FADH2, so that's going to give us 30 ATP. So now we can sum up. We have 93 ATP coming from NADH, 30 ATP coming from FADH2, and 8 we got from the TCA cycle. So in total, we have 131 ATPs being produced from this one palmitate molecule. But there's something else we need to consider, and that is that in beta oxidation, it is not the fatty acid that is entering beta oxidation. It's indeed the fatty acyl CoA. All right. In other words, we have to activate the fatty acid, and this is the typical reaction for the activation: fatty acid plus CoA plus ATP to give fatty acyl CoA plus AMP plus PPI. And the enzyme that catalyzes this reaction is called fatty acyl CoA synthetase. All right, so fatty acyl CoA synthetase. And anytime you see an enzyme with the name synthetase, you know that it's going to be using ATP. And in this case, ATP is being converted to AMP plus PPI, which is pyrophosphate. So let's talk a little bit more about that. The ATP is being converted to AMP. So ATP is adenosine triphosphate. In other words, there are 3 phosphates. And AMP is adenosine monophosphate, which means it has 1 phosphate. So to go from ATP triphosphate to monophosphate, you have lost 2 phosphate. And this is the energy equivalent of 2 ATP molecules going to 2 ADP, because each ATP is going to lose 1 phosphate to become ADP. So it's the energy equivalent of that. So knowing this, we then say the net gain of ATP from palmitate is the total, which is 131, minus the 2 that we use to activate the palmitate in the first place. So you get 129. And that's your final answer, guys. All right. So if you got that answer, excellent. But please, you know, the answer 129 is not important. It's the journey. So you must have all your statements to get the marks. All right, so let's recap. Let's go back to the question. Calculate the net gain of ATP when palmitate is completely oxidized. All right, so if you didn't get 129 before, I mean, you should go now and try it again and see what you could do. All right, and basically this is the statement you want to have for this kind of calculation. So you show the general formula for the rungs of beta oxidation, n over 2 minus 1. And as I said before, palmitate, N is 16, number of carbons. So you get 7 rungs of beta oxidation. Each round of beta oxidation will give us 1 NADH, 1 FADH2, and 1 acetyl-CoA, except for the last round. So for palmitate, we get 7 NADH, 7 FADH2, and 8 acetyl-CoA. Remember, I told you the trick is here is that the number of acetyl-CoA will be 1 more than your NADH and FADH2. For every turn in the TCA cycle, 1 acetyl-CoA will give 3 NADH, 1 FADH2, and 1 ATP. Alright, we had 8 acetyl-CoA in this example, so we get 24 NADH, 8 FADH2, and 8 ATP. At this point, you have NADH and FADH2 from two sources, from the beta oxidation and as well as the TCA cycle. So when you reach here now, you should be summing up the number of NADH and the number of FADH2. So the amount of NADH we have will be 7 plus 24, so you're going to get 31. And the amount of FADH2 that you got will be 7 plus 8, 15. So you have 31 NADH and 15 FADH2. Now those NADH and FADH2 now, they have to give up their pair of the electrons to the electron transport chain, and via oxidative phosphorylation, one NADH is giving us 3 ATP, one FADH2 is generating 2 ATP. So in total, you have 31 NADH generating 93 ATP and 15 FADH2 generating 30 ATP. Alright, now remember we also had some ATP coming directly from the TCA cycle, so we sum that up. Alright, so the 8 plus the 93 plus the 30, we get a total amount of ATP as being 131. Alright, but that's not the final answer. The final answer is the net gain. So we have to consider that we used 2 ATP to activate the palmitate to palmitoyl-CoA. So we give the equation palmitate plus ATP plus CoA to give you palmitoyl-CoA plus AMP plus PPI. And you know that's a long chain, right? Anything longer than that has more than 12 carbons. Alright. So it's catalyzed by a long chain fatty acid CoA synthetase enzyme. And you make the statement that the activation of palmitate to palmitoyl-CoA consumes an energy equivalent of 2 ATP. Therefore, the net gain of ATP will be 131 minus 2, which is equal to 129. So remember, guys, it's not so much the end, but the journey. You must have a proper statement showing your relevant formula, showing the different pathways that are involved, and justifying why you're getting this number. It's very important that you do that. So there are some other things that we need to consider. For instance, let's look at the first enzyme in beta oxidation, that acyl-CoA dehydrogenase. Now, acyl-CoA dehydrogenase has a prosthetic group on it called FAD. Now, when the FAD gains electrons, it becomes FADH2. And normally we stop there and we just talk about FADH2. But if you look in some textbooks, you'll see something called QH2. And that's fine. And what they have done is gone the extra step, which is that when FAD becomes FADH2, it's a prosthetic group, it's on the enzyme. To regenerate the original enzyme, the FADH2 will have to go back to FAD. To do that, it will transfer its pair of electrons to Q, which is ubiquinone, and then Q becomes QH2, which is ubiquinol. Alright. The other thing now, you see that there's some new numbers, and I'm telling you that one NADH will give you 2.5 ATP, and one FADH2 will give you 1.5 ATP. And that's based on the PO ratio, which is the number of phosphorylations of ADP in relation to the number of molecules of oxygen being reduced. Alright, or in another way to look at it is that these numbers were derived from the fact that for every 4 protons that leave the intermembrane space of the mitochondria and passes through ATP synthase into the matrix, 1 ATP is formed. So based on those numbers, that's where you're getting 2.5 and 1.5. So you might see some textbooks using those numbers. And if you use those numbers, but then you have to plug it back into the calculations before, and instead of multiplying 31, which was the number of NADH, by 3, you're going to be now multiplying by 2.5. And likewise, instead of saying you had 15 FADH2, instead of multiplying by 2, you're going to be multiplying by 1.5. The 8 ATPs that came from the Krebs cycle remain the same. And when you add that up, you're going to get a new number of 108. And that'll be a new total of ATP. And then to get the net gain now, you're going to minus the 2 that you used to activate palmitate. So you're going to end up with 106 ATP. All right, but for my exam, guys, you could use 1 NADH is equal to 3 ATP and 1 FADH2 is equal to 2 ATP. That's fine. All right. Now, the calculations that we are doing will involve even chain fatty acids. All right, if you have an odd chain fatty acid, then you have some other things to consider. For instance, the final round of beta oxidation will yield a 3-carbon fragment called propionyl-CoA. So this will happen for all odd chain fatty acids. And when you get propionyl-CoA, but then you're going to have to use some additional enzymes to convert the propionyl-CoA to acetyl-CoA. All right, but that's not for our syllabus right now. All right, another thing is that yes, beta oxidation for animals, most of it is taking place in the mitochondrial matrix, but you know, for very long chain fatty acids, and these are fatty acids that have a carbon length of more than 20 carbons, the beta oxidation of these fatty acids, they start in the peroxisome. Now, the beta oxidation in the peroxisome is very similar to the beta oxidation in the mitochondria, except for that first reaction. Now, in the mitochondria, that first reaction, you would have used acyl-CoA dehydrogenase. Well, in the peroxisome, you use acyl-CoA oxidase. And the difference here is that instead of transferring the electrons to ubiquinone to get QH2, which is ubiquinol in the mitochondria, in the peroxisome, the electrons are transferred to molecular oxygen, and you have hydrogen peroxide H2O2 being formed, which is readily broken down by another enzyme called catalase. All right. Now the thing is that the very long chain fatty acids, when they go to the peroxisomes, they are not completely oxidized. Basically, the peroxisome is acting as a shortening chain mechanism. So what it's basically doing is that it's going to be removing 2 carbons, 2 carbons, 2 carbons. But when the fatty acid gets to a smaller length, all right, suitable length, it's going to be then sent to the mitochondria for the complete oxidation to take place. So for animals, the peroxisomes don't really do a complete oxidation of these long chain fatty acids. It brings them down to a smaller size, and then they are sent to the mitochondria. All right. You might see a different relationship with plants, though, where the bulk of beta oxidation takes place in the peroxisomes and the glyoxysomes. You can read a little bit more about that. Very interesting stuff. Now, if you have an unsaturated fatty acid, and an unsaturated fatty acid is a fatty acid that has at least one double bond. Well, in that case, you have 2 additional steps. You have an isomerization, and the reason for that is because you know, the double bonds in a naturally occurring unsaturated fatty acid will be in the cis form. Well, you have to isomerize that cis form into the trans form. And the other thing you have to do is to do a NADPH dependent reduction. All right, and because of these 2 reactions, unsaturated fatty acids yields less free energy than saturated fatty acids. All right. Now, I'm not saying go and eat a whole set of saturated fatty acid because they give you more energy. That's not a good plan. All right, because you all know the health risks, like for cardiovascular health risks and so on, is much higher when you eat a diet that is rich in saturated fats as opposed to unsaturated fat. So please, although you're getting less energy, it's still healthier for you. All right, so we were talking all this time about beta oxidation. I just want to point out that there are 2 other types of oxidation. The first one I want to mention is alpha oxidation. Now, alpha oxidation occurs in the peroxisome. For alpha oxidation, what's happening there? These are for fatty acids or fatty acid CoAs that have a methyl group on the beta carbon. And remember, the beta carbon is the 3rd carbon from the acyl end. All right. So what happens is that if you have a methyl group there on the beta carbon, well, then you can't do beta oxidation. You have to remove that methyl group. So you do alpha oxidation instead. You see that happening. The most popular fatty acid that comes to mind will be phytanic acid, all right, or phytanate, all right. and that is a fatty acid that is derived from breaking down chlorophyll. So you'll see this so this is particularly abundant in plant-rich diets. So you're gonna have a lot of alpha oxidation taking place there in the peroxisome, all right, to break down that fatty acid. The other one, you might be seeing this as a strange looking W, and that's actually the Greek lowercase letter that stands for omega. So that's omega oxidation. Now for animals and for humans, omega oxidation is a minor form of oxidizing fat, so it plays a minor role. All right, it's significant when you have diseases such as MCAD deficiency, which is medium chain acyl CoA dehydrogenase deficiency, and in these cases, the patient's beta oxidation of medium chain fatty acids are compromised because he has this deficiency, and because of that, the medium chain fatty acids are diverted to the endoplasmic reticulum, where omega oxidation takes place. And basically in omega oxidation, you have oxidation taking place at the omega carbon, and this gives rise to dicarboxylic acids and so on in the blood and so on. All right, so here are some practice questions, people. So in the first one, you're going to be looking at a 6 carbon saturated fatty acid, and the other one is a 12 carbon saturated fatty acid, and basically you're going to be doing the calculations like how I showed you. So please go back to the statement if you didn't write it down as yet, and make your statement for these examples mirror what I have done, and once you go through these steps like how I did it, you're going to get the answer. So I have even given you the answers. So for the first one, you should get 44 ATP, and for the second answer, it should be 95 ATP. And remember, the answer itself, not that important, it's the journey. So you need to show proper statements and so on if you want to get all your marks. So please have a go at it. Let me know if the video was useful or not, and if you got your answers. All right, so again, study hard, study smart. Please like, subscribe, and comment on the videos. And good luck, guys. We'll talk soon. Take care. Bye.